All right, hello everyone. My name is Dimi Racordon, and I'm joined here by my friend Eugene Flesselle. The both of us are part of LAMP, the research group leading the development of Scala, as you know. And today we're proposing to take a quick look at other programming languages to figure out if there is anything we can borrow or shamefully steal to improve Scala. But before we start, I have a little confession to make. But I think it's fair to say that I'm a Scala contributor, being at LAMP and all of that. I have to say that I remain a bit too stubborn to consider Scala my first language. So I'm still somewhat of an outsider. And so that means I would not be very surprised if some of the arguments I will make seems a bit alien. And I'm also a very opinionated person. So I would be surprised if I don't annoy you a little bit, at very least a little. But I think this talk can be seen as an opportunity to look at Scala through the eyes of someone coming with a slightly different background than the usual Scala developers. And also, I brought Eugene here, who's the actual Scala insider. So if I start speaking too much nonsense, he will just stop me, so don't worry, you're in good company. So what do we want to do here? And to introduce the sort of mindset that we will have for this talk, I want to first look at this function. It's not written in Scala, it's written in Swift. And I picked this function from an actual code base. The purpose of this function is not really relevant, but what's relevant is that it's real code. So it's code that you could find in an actual Swift code base out there. Now, the interesting bit is here. In Swift, we can use pattern matching in the condition of an if statement. So here we're saying that the condition is satisfied if the pattern matches. And we can also have multiple conditions separated by comma. So I have another match here. And so this will be checked only if the first match succeeds. And of course, I need all of the conditions to succeed for the then branch to go. And I can mix in good old Boolean expressions, obviously. Now, syntax is large part a matter of taste and of habit, so I would understand if you think this is super ugly and you don't want to have anything to do with it. But as a language designer, I think it's important to look at this kind of piece of code and wonder if there is something beyond syntax that could be useful in a larger context, for instance, in the context of Scala. And I think there is. I think this part here is interesting, because this second match couldn't be merged into the first one in Swift. The problem is that the scrutiny of this match is using the value, or it's using the result of an operation applied on the value that I extracted from the previous match. And there is simply no way to write that in Swift without doing multiple matches. And this is interesting to do that here, because if any of these conditions fail, I want to run this long assignment, and I don't want to repeat this long assignment. But if I only had nested if expressions, like the regular intuitive one, then I would have to duplicate this long line. And this is something that I don't want to do because it will eventually bite me when I want to do a refactoring.
Well, of course, similar situations can come up in Scala as well. And unlike Swift, we have custom definition of unapplied methods, which means you can come up with some clever definition which will allow you to compose the two patterns, interleaving this trait declaration computation without requiring these subsequent cases. But this is maybe a bit contrived and not as straightforward as it could be. So we can copy Swift. As of the latest nightly, i.e. a few hours ago, you can now import experimental subcases. So similarly to Swift, you would start with a normal match expression, your usual outer case, and then introduce a submatch with the if keyword, similar to a Boolean guard we already have. So you can then continue your submatch similarly to a usual match, except it does not need to be total. If we do not match the submatch, we'll just continue to the outer case. So that's great. We can do what Swift can, but we can do more. For example, we can have multiple subcases for some common outer case, each with their different right-hand side. So generally speaking, we can remove the duplication of the default case, which we would have had to duplicate until now if there was no way to backtrack to the outer match expression if there is no match in the inner case. Another alternative that we could already do would be to duplicate the outer pattern for both of the different sub-patterns. So either you duplicate the outer pattern or the default case. Moreover, the sub-match expressions allow you to interleave pattern extractors and computation for the scrutiny of the sub-match. Of course, you can do so with some arbitrary nesting of sub-sub-sub matches and interleave if guards wherever you please. So generally speaking, this is our idea for this talk, to see if there are some cute patterns or design approaches from other languages which we can maybe easily or not so easily try to adapt to Scala.
Exactly. So this was a sort of mise en bouche, right? It was an easy one. For the remainder of the talk, we will need to set up some contexts. And for that, we'll start with a brief critique of our beloved collection library. And then we'll discuss some alternatives to collection libraries that are more based on type classes approach coming from Rust and Swift and C++. And finally, we'll look at open challenges with this design seen through the context of Scala. So generic programming. That's a topic that's very close to my heart. And as most people coming from systems programming, I borrow my definition from Alex Stepanov, who is the father of the C++ standard library. And he gave this definition that generic programming is the paradigm of expressing algorithms in terms of the properties of the data structure on which they operate without loss of efficiency. And this part is very, very important for people who care about performance, and I think everyone should care about performance, actually. But this is also core to this zero-cost abstraction principle, which is a phrase I'm sure you've heard from your C++ or Rust colleague. And in a nutshell, that means that if you use abstractions, it should not have an impact on the runtime execution of your program. It should be as fast as if you have not used no abstraction at all, even if you have written your program in assembly. Now, of course, if you're on the JVM, it's a bit difficult to reach that goal, but at the very least, we can aspire to this zero-cost abstraction principle. And to get a sense of what I'm saying in the context of Scala, we can look at this function here. So it's a partitioning function. It's taking an array here that's assumed to be sorted according to some ordering. And the function is finding the position of the partition on the right of the array in which elements satisfy a particular predicate. And this is a very, very simple algorithm. I'm sure you all know how to do a binary search. We split the array in half. We look at the midpoints. That tells us if we need to look at the right or on the left, and we repeat this process until we pinpoint the position. So for instance, if I start here looking for elements greater than 5 in this array, I look at the midpoint. It's 9. I need to go left. Then 4. I need to go right. 9. I need to go left. I'm done because there's no more elements to look, and I finish with 2. And well, this is the result. Now, obviously, this algorithm has log n complexity, and that's surprising. This is binary search. But more specifically, it performs log n applications of the function that is passed as a parameter. And that's the most important information I need to understand the complexity of the algorithm. It's not just log n. It's log n application of this is on RHS operation. The other stuff that the function is doing is in constant time, so I don't care that much about it. Now, if I want to apply generic programming, I need to abstract over something. So let's say I need to do my partition algorithm on strings, because why not? And I'm in luck because the exact same implementation works, so I just need to abstract over the data structure that I need to use. So how can we do that? Well, I guess many of you will write this function. So I've used seek here, which is an upper bound for finite ordered sequence in our standard library. But I would claim that it's a bit wrong here, because if we look at the documentation of seek, we see that nothing is said about the complexity of apply and length. And those operations are very important for our algorithm. They could dictate the complexity here. So before it was constant time, so I didn't care, but now I do care, because if I try to run this algorithm with a list or linear indexing, which would be terrible for this algorithm, it would change the complexity. So I have two ways to fix that. I can either change the documentation to reflect this change, or I could use a tighter bound. And we are lucky because there is such a bound in the standard library, and it's called an index seek. And an index seek refines a seek with semantic requirements that apply and length be efficient. Now, if you allow me to be a little pedantic, I think it would be best if the documentation was more specific about what efficient means. But I think it's fair to say that the author were thinking about like constant time or amortized constant time or something along these lines. But this is actually a pet peeve I have with the documentation of the collection library. It's often very, very difficult to get a sense of the complexity of the algorithms because the documentation is shy and because looking at the code itself requires to go through so many indirections, factories, mixins, and so on. I just cannot follow. So if we had to steal something from C++ or the STL specifically, would be better documentation of complexities.
Sure. We can always improve documentation. But other than that, all we've done here is good old subtyping polymorphism, which I imagine almost all Scala users are very well familiar with. Still, there are some limitations. For example, if you recall our original algorithm, which we wanted to apply to arrays, we are still able to do so, but the compiler will now generate a warning telling us that an implicit conversion has occurred from Java's arrays to Scala's index sequences. So if we look a bit what this exact conversion is doing, it happens to be doing a copy of the underlying array, which would be linear in time, which Dimi here would complain is unacceptable. So I will accept to define an array sequence class in Scala, wrapping the Java arrays into my class. Or I skipped over the part where I cannot just tell Java to make very primitive a subtype of my Scala class simply because we have no control over the parents of the class we do not own. And in particular, certainly not those from Java. So here, we're able to define our adapter without doing a linear pass, but as I'm sure you all well know, adapters don't scale particularly well. Consider, for example, a flattened function, which simply transforms a sequence of sequences into one sequence by combining all of the inner sequences. And suppose that we want to apply it to arrays once again. I'm not sure why one would use arrays, but Dimi seems to be motivated. If we try to use our adapters once again, we would need to do a linear pass over the outer collection to wrap each of the inner collections. So if we're really motivated, we can now define a wrapper for array of array sequences. But perhaps this is getting a bit unreasonable. We'll see later what we can do about that. In short, the problem is that with subtyping or inheritance, we cannot retroactively say that an array is an index sequence. Another issue is that consider Java's serializable primitive interface, which we are using here to define a method writing said item to an output stream. It just so happens that Scala's list class extends this Java serializable interface, which means we're able to call our save function with a list of integers. So far, so good. We're able to write this list to our output stream. However, the type system will also allow calling save with a list of objects that are not serializable, such as this one or, say, a function. That's because we said our class extends serializable independently of the type of elements to which it is applied. If we chose to instead say list does not extend the interface, we would then not be able to serialize any kind of lists. So, in short, to extend or not to extend is too coarse of a granularity for lists if that depends on the serializability of the elements themselves.
And if I can pile on with even another problem, I would say that it's a bit difficult with inheritance-based API to uncouple algorithm from their data structures. So let's say we take my partition index algorithm and I want to insert it in the standard library. We have unfrozen the standard library. It's great. So where should the algorithm go? I picked indexing before because I said I wanted to have efficient indexing, but it seems looking at this hierarchy, which is the hierarchy of our immutable collections, that maybe it could perhaps make sense on seq map. So again, the documentation is not very verbose about what seq maps are, but it's a map, so it should have constant time indexing. Spoiler alert, it doesn't, because list map has linear indexing, which makes me wonder why this data type even exists? Is it a map? But okay, moving on. Other implementations do have efficient indexing, so the ID at least holds water. But now I have an issue because I have two candidates and their list parents is not a valid place to implement my partition algorithm. So either I need to duplicate code or I need to do God knows what kind of tricks to try to pipe my things through factories and whatnot to avoid duplicating this code, which is certainly something that I don't want to do. I want to do what Stepanov said. I want to express my algorithm in terms of properties, and I don't want to have to care about this hierarchy. So none of what we're seeing here is particularly groundbreaking. I'm sure you've already heard about all of these issues. They've been well studied, and so on and so forth. But I think it provides background for what kind of motivations we want to explore here and what we can look into in other programming languages. And first up, C++. Don't worry, I don't require you to read all of this code. I'm sure this audience is not particularly keen on this language. And you can just trust me. This is the same algorithm as before. I promise. But there's a few things that are interesting to look at. So for instance, first up here, these two parameters here, they represent a collection. So this is a beginning and the end of the collection. And these are called iterators in C++. It's a bit different than what we call an iterator in Scala. In C++, an iterator is a position inside a collection and a position that also confers access to the element at that position. And we can see that here with this star operator. It looks like dereferencing, but it's a bit more abstract. And also we can advance iterators to other position. And this is what this std advance function is doing. It's another generic algorithm that comes from the standard library. And it roughly corresponds to what we were doing when we were adding a value to positions in Scala. But it's a bit more abstract here because I do not require this iterator to be an integer. And there's another algorithm that I'm using here is std distance that is roughly corresponding to the length that we had. But again, we are abstracting over the specific implementation. Now what's interesting is that these two operations are the requirements of our algorithm, and they match what we got from indexing. So what we need really to express this algorithm is just to have these operations. They don't have to be implemented by an abstract class. They can be implemented by anything we want, just like free functions even. So at call side, it looks like that in C++. I can instantiate, for instance, my partitioning algorithm for pointers into an array, because pointers happen to satisfy all the requirements that I've mentioned. And what's nice about this approach is I can use the exact same setup to run my algorithm on slices. I just have to advance the start of my array with this infamous pointer arithmetics that I'm sure is very scary for the current audience. But the point is that I have a lot of freedom here to express these operations as long as I satisfy the requirements of the algorithm. And I can satisfy these requirements with any data type I like. Now, we will not do that in C++. It will be verbose, and we don't like C++. So let's pick a nicer programming language. Let's look at Rust. So Rust doesn't model containers the same way C++ does, but it has a very cool type system that we can leverage to do similar things. So in Rust, we have traits, which define type classes, and that's roughly, a type class is roughly a collection of requirements. And here, for instance, I've defined this trait stridable for representing types that can be offset and measured.
Where for the Scala people among us, there is implicitly a self parameter, which we would typically write as an explicit type parameter of the trait.
Thank you for the precision. Then I can use this as a sort of context bound to require that this type parameter here has a type class instance of stridable. I can also add another context bound for copy. This is to appease the Rust power checker. And I can use this index thing that comes from the standard library. It's basically describing types having an apply method. And then this funny looking thing is to describe a function. It's funny looking because Rust needs to care a little more than Scala about resource management. But essentially, this is just describing a function interface. Now, because stridable is not an abstract class that I need to inherit at the point of definition, I can define retroactively as many instances of stridable as I want. So for instance, here I can say that unsigned integers are stridable. And obviously, I'm not the author of unsigned integers. This is part of the standard library. But I'm able to work around the first issue that we had before. I can retroactively add things.
Where an impl would be what you guys know as a given instance in Scala.
Precisely. Now, all of these shenanigans allow the type checker to ensure that these various operations are well defined. And, well, separate checking is not surprising for this audience, but if you want to one-up your C++ colleagues, you can just show this kind of code and they will be amazed because C++ templates are just glorified macros, right? So this is very nice. We have separate checking in Rust. This is even cited often as better than the borrow checker if you come from C++ going to C++. But I would say if you're a Scala developer, you look at this signature and you say, well, this is a bit involved, right? I really prefer the Scala one, and I would agree with you. So part of the complexity here is due to Rust attention to resource management, as I said, but there are better abstractions that we could build. And for that, I want to look at a bit at Swift. So Swift also relies heavily on type classes, and it does happen to have a collection trait in its library, and it looks something like that. This is exactly the requirements that we have already discussed, so let's not spend too much time on it. So this is roughly the equivalent of seek for Scala. Now we can define refinements of type classes or protocols in Swift here. So I'm doing that. I'm defining random access collections, which are collections, but they also have these additional requirements that allows me to offset a position by any arbitrary integer. And I also want to add a semantic requirement that this apply method should be in constant time. So now it matches the index seek that we had before.
Where refinement in Scala would be encoded as inheritance, not from the types implemented in the classes, but among the hierarchy of classes themselves.
Now, putting all pieces together, we can implement the same algorithm or running example. And Swift supports Scala-like extension methods, and so we can have the nice extension method syntax. This is all very nice, and it looks pretty good, I would say. So can we do something similar in Scala?
Right. As a member of the class of Scala people, I can assure you we do. We've had enough of this, and we can come back a bit to Scala. So, in fact, we would do this without a special built-in construct, but just as a normal trait definition, which happens to be parameterized by some parameter called self by convention. But we could decide it to call anything we'd like. There's nothing special about it. We also happen to use a type parameter for the type of elements in the collection, perhaps unsurprisingly. More surprisingly, we choose to add a type member for the type of indices by which the collection is indexed. We'll come back to the motivation for this later, but for now, it's worth noting that we choose to use a parameter for one and a type member for the other. The member could be selected on an instance of the trait, similarly that we would select any other runtime field of the trait. So we can now define a function which is defined for any t with an implementation of this class by taking it as a using parameter, also known as an implicit parameter. So assuming we have defined a fold left method in terms of the previous operations from the class, we can now sum the elements from a collection of integers as one might expect. So bear with me now, we're introducing a bit of syntactic sugar which will be useful later. First, we can use, similarly to Swift or Rust, a context-bound syntax which expects not a special construct which happens to be a type class in a built-in sense, but just a type that is expecting to be applied to another parameter, which we can write here as a type lambda with this double arrow thing. For convenience, we can define an alias of this lambda, but otherwise, this is the same as before. In short, we just are saying that our function is defined for any t that is a collection of integers. So back to our original motivating example. I copied over Dimi's code because this is a bit too complicated for me, but assuming the implementation is correct, we can just replace our usages of the methods built in from the array with applications of those found in the random access collection class. So back to our original motivations. We can now do retroactive conformance to the trait of types that are collections by just declaring a given instance at any point in our program, which need not be necessarily at the point of the definition of the type. Furthermore, we can say that a type or a collection is serializable only when its elements are, with a conditional given instance. Sadly, there are some new issues. So recall our flattened example, which with subtyping expected quite simply a sequence of sequences, which we could call with a outer sequence whose inner sequences were not necessarily of the exact same type, as long as they were all subtypes, or in this case, subclasses of the sequence trait. In the context of type classes, things get a little bit more complicated. We say that we expect any value self of type B, where B is a collection of A, and A is a collection of T, our type of elements. We're still able to apply our functions to the same arguments in the type class-based approach, because there is a common supertype of array sequence and range for which there exists an instance or a witness that this supertype is a collection. However, if we were to try to apply this same algorithm with an inner sequence that is an array, for which there exists a witness that it is a collection, we would run into trouble. That is because the least upper bound of our inner sequences is, as you can see here, an array of integers or a range. But there's no simple base type that is common to both those types. Or more significantly, there is no common supertype for which there is one instance of the collection type class. Intuitively, we see that our flattened function only accepts one witness that the A's are collections. And here we have arrays and ranges which may both be collections, but for which there is no common instance. So there would be no way for us to pass both of those to the flattened function.
But we can do better in Swift. So we can use this funny-looking type here, any collection of T. And in Swift, it's used to denote what we call an existential container. So it's any value whose type conforms to the collection trait. So translated in Scala, this is wrapping a value with a type class instance for its type. And the cool trick is that the existential container exposes the API of the wrapped instance. So we can call the reduce method here, which corresponds to fold left. And we can also unwrap implicitly the value automatically to apply this append all method here. So append contents of is the append all method, which of course in Swift is defined in terms of type classes. So can you do something like that in Scala?
Surely we must be able to. So let's try to unpack a little bit what is going on there. Once again, we would implement this in Scala with no additional built-in construct, but with a trait. So here we're saying that our container of collections is just some trait that has a type member for the current value that is contained in this container, but crucially, we're not using a parameter. Because if we did, at our use site of the sequence of collections or containers of collections, we would need to apply the parameter of the outer sequence to the same parameter value, which defeats our original purpose, which was that each inner collection should be able to have a different type. So we do so here by making it a type member, which depends on the current instance of this any collection trait. Then, as expected, we have our pair of value of that type and witness that that type is indeed a collection. So if we go back, we can construct an instance of this trait for any value v with a witness that this v is a collection and pack all of these parameters as fields of our trait. For example, we can put our array in an any collection container by implicitly capturing the witness that it is indeed a collection. Now we can generalize this to arbitrary classes. This is exactly the same code as before, except that instead of having a witness that value is a collection, we now have that value is a p, where p is a parameter of the container. So we express here that p is a type class in Scala by just asking that it be higher kinded, which we would write with this bracket underscore notation, which simply means that it is yet to be applied to the type of values to obtain a proper kind of type. But otherwise, the same thing as before, and we can put, once again, our array in this container for the P that is instantiated to collections of integers. So how do we use these traits? Starting off with everything explicit, we can extract both components, the value and the witness, out of this container. But crucially, we can see that the type of the first projection is dependent on the container. So its type is XS.value. Similarly, we see that the type of the witness is for that XS.value as well. So we're able to combine them to actually use the operations of the class. But this is awfully explicit, so of course, we would want to do a lot less than that. First, we can inline V, and then elide the explicit mention of W, and simply select length on the value using some fancy implicit resolution reasoning, which happens to find the witness in XS, because the type of XS.value gives us the path to the witness, as we can see in its type. Finally, we would also like to elide this dot value selection, which we can do easily with a one-line change in the compiler, which is part of our latest Scala improvement process proposal. So we can build a container and pick it apart, but can we actually do flattening of sequences of sequences? So what's going on here? We're asking self to be of type T, where T is a collection, where all elements are containers of collections. But crucially, each container now contains its own witness, which need not be for the same type of values. And we can now successfully flatten an array sequence which contains both an array and a range, each capturing their own witness. If you'd like more details, like a lot of implicit resolution stuff we've skipped over here, feel free to look at the MPLR paper.
Okay, you can do it. That's very nice. It's compelling for Scala. Yeah?
So when you do this wrapping, you have to traverse the original collection, right? So you're adding a linear amount of work.
If you're passing the sequence of sequences to flattened, yes. But if you had worked in a type class-based approach from the get-go, presumably you would already have a sequence of containers of sequences.
Yeah, because if you wanted to build the iterative sequence from the beginning, then you would have to have done that. Or you would have a just collection of arbitrary things that you don't know what they are. Like they would be collections of any, for instance.
But of course, there's some extra cost here anyway, because we are building pairs and packing the witness each time.
So back to the collection traits, some of you might find a bit puzzling that we need to abstract over this index thing. Like indices are integers, right? Everyone knows that. So why are we insisting on this index thinking? Well, that's because insisting on zero-based indices actually makes these traits harder to implement and use in most situations. So think about lists, for instance. I complained before that lists have linear indexing, right? And it's terrible for like the partition index. Well, in C++, they do not have linear indexing, so how come? Well, we can just use lists themselves as their own index. You remember what an index needs? An index needs to give access to the element at that position, and it also needs to be able to be advanced to the next position, which is certainly something we can do with lists. And so if we do that, what's nice is that now we get constant time indexing for lists, and we get to use a lot more algorithms with reasonable complexity, such as partitioning index, which is now log linear instead of n squared. I would claim that it's an improvement. And even if you have integer indices, it might be interesting to not have them be zero-based in all cases. That would be nice if you want to implement divide and conquer algorithm. So for instance, here I want to express a function that is collecting all the indices of elements that satisfy a predicate, and I want to use the awesome gears library that was briefly introduced yesterday with Nien's talk to do it concurrently when the collection is too large. And so I'm splitting my collection in two. In the case it has more than 64 elements, and then I'm running this in parallel. And of course, this concurrent execution will return their own indices, and they must make sense in the whole collection, lest I would have to implement some kind of expensive and sophisticated adaptation of the indices, and obviously I don't want to do that. So this is here justifying these indices, which is also a concept that I think we could bring back in the Scala library. But we have used slice here, and this might be the final boss for this talk. So how slices are expressed in Swift? Well, in Swift, it's a bit simple. We can define here the struct, sort of like a case class, and it's parameterized over the collection of which I am a slice. I require this a collection to be a collection with a context bound, and then the slice itself is reference to the base and the two elements, the two positions, like the start and the end of the slice. And then I can define that the slice are themselves collections, and they obviously have the same indices as the collection, as I justified before, and they obviously have the same elements of the collection. Now, let's try to do that in Scala.
Mm-hmm. So once again, we can do it, but it does admittedly get a little bit complicated at this point. So I hope you're ready for it. So if we try to naively translate what we were doing in Swift, we would create a class for the slices, take free parameters for the base, start, and end, similarly to what we were doing in Swift, and additionally require an instance that this base is a collection, which, by the way, gives us the type of indices. Next, we would want to say that all slices are collection. First of all, Swift has this interesting syntax where we here have an implicitly quantified for all base and for all type of elements. In Scala, we would need to do so explicitly and say that for all B and type of elements, slice of B is indeed a collection with that type of elements. We're able to implement the operations of the collection. For example, start is trivially defined using the field from the class, and index after can be defined using the operations found in the witness captured by the class. But crucially, we're defining these operations here by using either the value or the witness is found in self, whose type is an instance of the slice class. However, we do not have access to this self parameter at the point of the type definition for index. So how is Swift able to define it? Well, it just so happens, so yeah, obviously it's not in scope at this point. In Swift, it happens that to even be allowed to write slice of B, you need to assume that B is indeed a collection. So there is implicitly an extra constraint that B is a collection, which we here have explicitly named D. We can now use this instance to define the type of indices of the slice based on the witness that the inner base type is a collection. But we have a new error. The compiler will complain that the type of start found in the class is c.index, whereas we've defined index to be d.index. And rightfully so. But suppose we were to use these fancy unsafe constructs, maybe not so safely in this case, but let's try it. So in Scala, we can have local given instances. So let's say we want to see longs, which we've here aliased as small buffer, as collections of bytes. In our first inner scope for slice, we say that they are collections where we define indices to be shorts, because why not? And we were out of space for the slide. Next, we pack a long into this slice class. We escape this class into the outer scope, where we also happen to define that small buffers are collections of bytes, where we now say indices are bytes also. If we were to now use the start index, which was constructed under the assumption that indices are shorts, in the scope where we have said small buffers are collection where the indices is byte, we would obviously get a runtime error. So our compiler is right to reject our original definition. If we're really motivated, we can add another level of constraints to convince the compiler. So what we're doing here is requiring that the instance captured by slice be precisely the same one as the one available in the current context. So we want the C in slice to be the same as D, which we can do by refining or qualifying the type of the class slice to have a value C whose type is the singleton type D. So at this point, our code is going to compile and it's going to be safe, but things have gotten a little bit out of hands. If you're not lost, and type inference definitely is, and this is not usable as is. So we might be tempted to simplify things a bit. We can see that our class slice is not using C for anything other than the type of indices. So we might want to just use a good old type parameter. which we can do easily. Now our given instance is still conditional on D, but does not need these fancy refinements and can simply use the index or the type of indices found in D to, as the parameter for the class slice. But here we've done something a bit dangerous. So otherwise the implementation still compiles as before. So consider the same example as before, but now we happen to use the same type for the associated type index, both in the inner scope and the outer scope. But we may choose to not have the same implementation of the operations, for example, apply, which given an index returns an element of the collection. So for example, here we've decided to iterate over the bytes in the long from left to right or right to left. Who knows what this is doing, but different direction in both cases. Here there is nothing that is unsound because we've happened to define the associated type index as the same for the inner collection witness and the outer collection witness. So this is all accepted by the type checker. But this is not very consistent semantically speaking, and there's nothing to catch our mistake. So simplifying our original definition is not necessarily a good idea.
Okay, I think it's getting a bit complicated. Inference is tired, and I guess the audience is getting tired too, so maybe we should stop at this point. But let's wrap up and see what we've discovered. So what can we learn from our little walk into other languages? Well, sub-patterns, I think, is a nice addition, and we have actually implemented it. We have seen interesting ideas for maybe improving or providing an alternative to our collection library. And there's also this idea of existential containers, which we have also implemented and submitted as a Scala improvement proposal. And what can we innovate? Well, there is this problem with the type class instances and the associated type that Eugene has mentioned. And I think this is actually deserving a little more investigation, even from an academic side. But with that, we're closing. Thank you very much for your attention. And if you have time for a couple of questions, we are happy to take them.
No questions? Was it too easy?
We are unfortunately over time, not even on time. So I'm pretty sure Dimi and Eugene will take any questions you have outside.
Happy to do so.
So thank you both of you. And,
Thank you, everyone.